Welcome to the Deep Dive. We're here to cut through the noise, get you those essential insights from, well, pretty complex research. And today, we're plunging into the future of generative AI for vision. It's fascinating stuff. We're focusing on two really groundbreaking models that are pushing the boundaries, DINOv3 and SAM2.
Yeah, two big names right now.
Absolutely. And this deep dive, it's really tailor-made for you, our listener. Whether you're, just curious or maybe you're an AI researcher yourself, we want you to understand not just what these models do, but how they actually work.
Right, the mechanics, the design philosophy behind it.
Exactly. What makes them pick under the hood. That's our mission today. We'll explore their architectures, their training methods, performance.
And those implementation details, the nitty-gritty stuff that helps you see how you can maybe improve them or use them in your own work.
Precisely. And to do that, we've gone through the technical reports, the papers from the research groups behind DINOv3 and SAM2.
Pulled out the critical nuggets.
Yep, the most important bits. So where should we start? SAM2, maybe?
Sounds good. Let's unpack SAM2. So at its core, it's what they call a foundational model built for promptable segmentation.
Promptable segmentation.
Right.
Like the original SAM segment anything.
Exactly like SAM, but it takes those capabilities and extends them. And this is the key part. It works on both static images and dynamic videos.
Okay, so adding video, that sounds like more than just a small update.
Oh, it's a leap. Definitely. It's about understanding objects across time, not just in a single frame.
Yeah, temporal awareness.
Yeah.
That must unlock a lot of applications, right?
Huge. Think about AR, VR, robotics, autonomous driving.
Video editing, too, I imagine.
Absolutely. Anywhere you need to track objects as they move, change, interact over time. It's not just about finding the object in one picture anymore. That's the differentiator.
And how does it perform? Is it just about adding video, or is it better overall?
It's better. Significantly better segmentation accuracy. And it needs, get this, 3 times fewer interactions than older methods.
3 times fewer. For anyone doing interactive stuff, labeling, that's massive.
Yeah.
Less clicking.
Huge reduction in effort. And what's really impressive, it actually beats the original SAM on image benchmarks, too.
Wow, okay. So it's better on images, and it does video.
And it's faster. 6 times faster.
6 times, okay. That's quite something.
Yeah, and it works well across loads of zero-shot benchmarks, like 17 for video, 37 for single images, without needing specific fine-tuning for every single task.
That zero-shot capability is always impressive. And you mentioned the reports. Is the model itself accessible for researchers?
That's another big plus. It's released under permissive open licenses. Very open.
What does that include? Just the model weights?
More than that, the model checkpoints, definitely, but also the SAV dataset. That's the video dataset they created, which is massive in itself. And all the code for training, for the interactive demo, everything.
Fantastic for the community. Real transparency, accelerates research like crazy.
It really does. Okay, so that's SAM2. Now let's pivot. DINOv3.
Right, DINOv3. Different approach here, isn't it?
Completely different philosophy. It comes from the world of self-supervised learning, SSL.
Self-supervised, meaning no manual labels needed during pre-training.
Exactly. The core idea, the promise, is to get rid of that costly, time-consuming manual annotation step.
Which lets you scale up massively.
Precisely. Scale to enormous unlabeled datasets and build much larger architectures. DINOv3 is designed to learn really robust, general visual representations straight from raw pixels.
So it's aiming for versatility, a kind of universal visual understanding.
That's the goal. High versatility. It can be kept frozen, so no task-specific fine-tuning, and still get state-of-the-art results across a huge range of tasks. Image understanding, sure, but also complex 3D scene understanding.
So for a researcher, that means potentially one powerful model serving lots of different purposes.
Yeah.
Simplifying things downstream.
That's the vision. And it's not just one model either. It's like a family. There's this enormous 7 billion parameter version.
7 billion, okay.
Yeah, huge. But the knowledge in that giant model is then distilled down.
Distilled? Like compressed into smaller models.
Exactly. Into smaller, more efficient variants. VIT, small, base, large, even ComNext versions.
So you get the power, but adapted for different resource levels. Practical deployment.
Right, that multi-student distillation, they call it. It's key for making these massive models actually usable by more people, democratizing access.
Interesting. So 2 powerful models, different philosophies. As we dig deeper into the architecture, is there any common ground, anything they implicitly share?
Well, at a fundamental level, yeah. Both rely on really powerful image encoding. You need that base layer of understanding the image first.
Okay.
SAM2, for instance, it uses an MAE pre-trained Hyera image encoder.
MAE, mask autoencoders.
Yep, that's the self-supervised pre-training method, reconstructing masked image parts. And Hyera refers to its hierarchical structure. Gives you multi-scale features for the decoding part.
And that encoder is efficient.
Incredibly efficient. It only runs once for the whole interaction, even if it's a long video sequence. That's foundational for its real-time video performance.
Right. Run it once, use the features repeatedly, makes sense. And DINOv3.
Yeah.
It uses vision transformers, but pushes them further.
Absolutely. For that big 7B model, it uses a custom variant of the vision transformer, the VIT.
What's custom about it?
A key thing is the positional embeddings. They use axial ropey.
Rotary positional embedding.
Right. These help the model understand spatial relationships better without getting thrown off by where an object is. Helps learn consistent features across the image. And it also uses a specific regularization technique to stop positional artifacts from messing things up. That's critical for learning those really detailed, robust features across different scales. That's what gives it that versatility we talked about.
Okay, so this is where they really start to diverge. The architectural details that make them specialized. For SAM2, it's all about time, that temporal awareness. How does it actually track things frame to frame?
The core component is its mask decoder. It's lightweight and, importantly, promptable. It takes those image embeddings from the Hyera encoder, plus the user's prompts, points, boxes, maybe existing masks, and spits out segmentation masks for individual frames.
And it can be refined.
Crucially, yes. Especially for video, you need that interactivity. You can keep adding clicks frame by frame to improve the mask.
But how does it keep track between frames? You mentioned it seems almost like it knows what's coming.
Yeah, you picked up on that. It's fascinating. The frame embedding that goes into the decoder isn't just the raw image encoding, it's conditioned.
Conditioned on what?
On memories of past predictions, and also frames that were previously prompted by the user.
Okay, past memories make sense, but you said from the future almost.
Well, during training, yeah. Their data engine is clever. It allows the model to learn using information from later frames in a sequence relative to the current one being processed.
Whoa. Okay, that's not predicting the future runtime, obviously.
No, not predicting the future during inference. But the training process lets it learn really robust correspondences because it's seen, effectively, how things evolve.
That's a clever training strategy. So how does this memory system actually work? How's it built?
There's a memory encoder. It creates these memories from current predictions and stores them. It uses a FIFO queue first in, first out for, say, the last and recent frames.
Okay.
And there's a separate queue just for the frames the user actually prompted.
2 queues. And what's in the memory? Just feature maps?
Mostly spatial feature maps, yeah. But also something called object pointers.
Object pointers.
Yeah, these are lightweight vectors that come from the mask decoder's output. They capture higher level semantic info, like what the object is, not just where.
Ah.
And then the memory attention mechanism cross-attends to both the spatial features and these object pointers. It remembers where something was and what it was. Helps keep track better.
That dual memory sounds robust. And you mentioned temporal position.
Right. It embeds temporal position info into the recent frame memories. Helps capture short-term motion.
But not for the prompted frames. Why the difference?
That's a nuanced choice. The training signal for prompted frames is sparser, right? You only get clicks on a few frames. So trying to generalize complex temporal relationships from those sparse prompts is harder. They found it's more robust to focus the temporal encoding on the recent dense predictions.
Okay, that makes sense. Focus where the signal is strongest. Really deep dive into SAM2's temporal side there. Let's switch back to DINOv3. You mentioned this challenge of dense feature stability at scale and something called gram anchoring. What's that all about?
Yeah, this is super important for DINOv3, especially that 7B model. The problem they found is, as you scale up and train for a long time, global performance, like image classification, keeps getting better. But dense prediction tasks, like segmentation at the pixel level, surprisingly start getting worse after a certain point, maybe 200,000 iterations or so.
Worse? How does that show up?
You see it in things like noisy similarity maps between patches. The patch level consistency degrades, like the cosine similarity between the global CLS token and individual patch features starts increasing.
Mean the features become less localized, less useful for fine-grained stuff.
Exactly. The features sort of blur together conceptually, losing that sharp local detail needed for dense tasks. Scaling up broke the fine details.
So gram anchoring is the fix. How does it work? And why the Graham matrix? That sounds mathematical.
It is, but it's elegant. Graham anchoring introduces a new loss function. It operates on the Graham matrix of the patch features.
Okay, define Graham matrix in this context.
It's basically a matrix showing all the pairwise dot products between the feature vectors of all the patches in an image, so it captures the relationships or similarities between all pairs of local features.
Right, the structure of similarities.
Exactly. And the goal of the loss function is to push the student model's Graham matrix, one being trained, towards the Graham matrix of an earlier version of the model, a Graham teacher, which had better dense properties.
So you're not forcing the features themselves to match the old ones, but their relationships.
Precisely. That's the key insight. Think of it like dancers on a stage.
Okay.
If you try to force each dancer into an exact spot, fixing individual features, they can't move freely. But if you enforce the relationships between them, their relative positions, the overall choreography, the Graham matrix structure, each dancer can still adapt and move while the overall structure stays coherent.
That's a great analogy. It allows flexibility while preserving the important structure.
Exactly. It lets local features evolve, but preserves the structure of similarities, stops that degradation without being too rigid.
And is this Graham anchoring running all the time during training?
Usually not. It's often applied as a refinement step, maybe after a million iterations or so.
Yeah.
They apply this Graham objective typically on global crops of the image.
And it can actually repair degraded features.
Remarkably, yes. It often leads to immediate improvements on dense tasks. They even use higher resolution features for the Graham teacher during this step.
Using a better teacher to guide the refinement.
Right. Boosts dense prediction accuracy even more, ensures you get robust feature correlations, even with complex high-res inputs.
So for researchers digging into the training loss itself, DINOv3 isn't just using one thing.
No, it's a mix. It uses an image-level dino loss, a patch-level IBOT loss, that's another SSL method for reconstructing mask tokens,
Okay.
and also a Colio regularizer. That encourages features within a batch to spread out uniformly. It's the sophisticated blend that leads to its robust learning.
The training and data strategies sound just as innovative as the architectures. SAM2's data engine. How do they even gather all that video data?
It was a huge effort. Their training used a mix of image and video data, and they simulated the interactive prompting process.
Simulated it. How?
They'd take short video sequences, like 8 frames, then randomly pick a couple of frames to simulate getting corrective clicks from a user. They'd use ground truth masks or clicks or bounding boxes as the initial prompts. This makes the model really good at handling real interactive use.
And the actual data collection. The SAV dataset.
Monumental task. They built this data engine with human annotators working with the model in the loop.
Model in the loop. So the model helps the annotators?
Exactly. And it got much better over time. They had 3 phases. Phase 1 took nearly 38 seconds per frame to annotate.
Wow, okay.
By phase 3, with the model helping more effectively, it was down to 4.5 seconds per frame.
4.5 seconds. That's incredible. Makes large-scale video annotation actually seem possible.
Totally. And they also did an extra fine-tuning stage just on longer 16-frame sequences, focusing on really tricky videos that needed more human edits to boost robustness on hard cases.
Makes sense. Now, DINOv3's approach to data and training sounds quite different, especially the learning rate thing.
Yeah, it's a major departure from typical large model training. First, the data scale is immense. Starts with something like 17 billion web images, public Instagram posts after moderation.
17 billion.
Yeah. Then they curate it carefully. There's a big balanced dataset, LVD1689M, made using clustering. Another dataset focused on relevance to downstream tasks using retrieval, plus standard public vision datasets.
A curated mix from a massive pool. And the training schedule. No cosine decay.
Right. Many models use complex learning rate schedules, like cosine decay, which means you need to know the total training steps in advance. That's hard with huge open-ended datasets.
Yeah, how do you know when you're done?
Exactly. So DINOv3 uses constant learning rates, constant weight decay, constant teacher EMA momentum.
Constant, how does that work?
It simplifies tuning massively. And critically, it means you can basically keep training as long as the performance is still improving. No fixed endpoint needed. It's a huge practical win for scaling SSL.
Okay, performance time. Head-to-head, SAM2 versus DINOv3, where do they shine?
SAM2 is the clear winner for interactive video object segmentation. That's its domain. It consistently gets better JNF scores, that metric combining region and contour accuracy, than prior state-of-the-art methods. both offline and online tests. It's built for video, and it excels there, a big step up.
And DINOv3, the generalist, how does its prowess show up?
Even without fine-tuning, it's incredibly versatile. That gram anchoring really pays off. You get sharper, less noisy, more semantically meaningful, dense features.
You mean it's good at?
Things like semantic segmentation. It outperforms competitors, even models using SAM2 features like spatial by a good margin on benchmarks like 80-20K. We're talking like 6 IOU points better.
That's a significant jump in segmentation accuracy.
Yeah. And it's also state-of-the-art in monocular depth estimation, understanding 3D from 2D images. Plus, it shows really strong 3D consistency, better than others at matching key points in 3D space, crucial for 3D reconstruction, pose estimation.
But the most surprising thing, maybe, is its video performance for an image model.
That's what's truly remarkable, I think. DINOv3, trained mainly on static images, shows strong temporal consistency. It actually outperforms dedicated video segmentation tracking methods on datasets like Davis and YouTube VOS.
How is that possible?
It suggests its learned features are so robust in general that they implicitly capture temporal dynamics. It's learned something fundamental about the visual world that translates across time, an emergent capability.
Wow. That points towards a really deep level of understanding.
Exactly. And that's why it can be used as a frozen backbone for so many tasks. Object detection like plain DTR, segmentation with mask-to-former, depth estimation like depth anything. It often hits state-of-the-art with fewer trainable parameters needed in the downstream model compared to specialized approaches. A real generalist workhorse.
Okay, thinking practically now. For the researchers listening who want to use these, how do you actually run them? Any key implementation details?
For SAM2, the key things for speed are that streaming approach for video and the encoder only running once per interaction. When you have multiple objects, it shares the main visual features but runs separate memory banks and mask decoders for each object.
Simple enough. Any downsides to that?
Well, the paper notes it as a limitation. There's no built-in communication between the trackers for different objects, so understanding complex interactions between objects could be an area for future work.
Okay. And DINOv3.
Yeah.
Especially that giant 7B model. How is its power made accessible?
That multi-student distillation pipeline is crucial. It lets them train multiple smaller student models simultaneously, sharing the expensive computation of the big teacher model across GPUs.
That's clever. Makes distillation much more efficient.
Yeah, it's a game changer for getting the power of huge models into smaller, deployable ones. Great for researchers.
And it handles different resolutions.
Yep. It's trained at lower res, like 256 by 256, but has a high-resolution adaptation step. So it generalizes well to lots of input sizes. Visually, they show it working even above 4K. Very flexible.
Crucial for generalist models. And linking vision to language, text prompts.
It can do that too. It can be aligned with a text encoder. It concatenates the mean pooled patch embeddings with the main CLS token. This aligns both the global summary, CLS, and the local patch features to text embeddings.
So you can use text to query specific regions or objects?
Exactly. Enables powerful zero-shot capabilities, bridging vision and language effectively.
Okay, we've covered the strengths, but limitations are important too.
Yeah.
Where does SAM2 still struggle? Where can researchers focus?
It's powerful, but yeah, edge cases exist. Abrupt shot changes in video can throw it off. Crowded scenes, long occlusions, really long videos where context might drift. Those can be tough. Also, very thin objects or really fast-moving details, and objects that look very similar and are close together can sometimes confuse it.
But the interactive nature helps there.
Absolutely. In most cases, a user can add a quick refinement click to get it back on track.
And DINOv3. Any quirks from its self-supervised massive scale training? You mentioned outliers.
Right. It's subtle, but researchers scaling these should know. They observed what they call feature dimension outliers. Not the patch outliers some models get. DINOv3 uses registers to handle those.
Okay, so different kind of outlier.
Yeah, these appear within the feature channels themselves. They don't seem to hurt inference much if you apply a final layer normalization, but fully understanding and mitigating them is an active research area for large model stability.
Good to know for those pushing the boundaries. And finally, we have to touch on the environmental costs. These models are huge.
It's a critical point. SAM2's training, 256 A100 GPUs for 108 hours. That's estimated around 3.9 metric tons of CO2 equivalent.
Okay. And DINOv3, with 9 million GPU hours.
Much larger footprint, estimated around 2,600 metric tons of CA2e.
Wow!
Yeah, that's roughly half the CO2 from all Paris-New York return flights in a single day. It's substantial.
Definitely highlights the trade-offs. Incredible capability, but a non-trivial environmental cost in development.
Absolutely. Something we need to keep wrestling with as a field.
So zooming out, the big picture. We've seen two really powerful but different paths forward in Vision AI.
Yeah. SAM 2. Specialized, efficient, interactive, king of promptable video segmentation, really nails that temporal consistency.
And DINOv3, the self-supervised generalist. A fundamental leap, producing these incredibly versatile features that work amazingly well across tons of tasks, even video, without specific fine-tuning.
Right. And for you, the researcher listening, this shows kind of a fork in the road, right? Are you building a purpose-built system or leveraging a foundational model? Either way, the innovations are in things like architecture, these clever training tricks like gram anchoring, efficient distillation, smart data engines.
Insights into problems like feature degradation, handling massive data,
Yeah.
optimizing for deployment.
Exactly. Those are the pathways for you to improve things further in your own work.
So a final thought to leave our listeners with. As these models get bigger, more general, what happens when a single frozen visual model can truly understand pretty much anything? Static images, complex video, what entirely new things might become possible then?
That's the exciting frontier, isn't it? Unforeseen capabilities emerging from true general understanding.
Something to think about. That's all for this deep dive.